Hi everyone, my name is Randy Yao. I'm a software engineer at Zillow, and following later on in this presentation will be Nikhil, and we're here to talk about how we at Zillow used AWS serverless technologies to build our 3D home project. First, we're going to talk about Zillow, our 3D home platform, and from there we'll take you through our journey starting from building from a traditional architecture, the limitations we encountered, and later iterating to more scalable and reliable serverless architecture powered by AWS step functions. By the end of this talk, we hope you understand some of the trade-offs we made, as well as the major benefits we achieved as a result of our transition. So Zillow's core objective is to arm home shoppers, renters, owners, the masses with the information needed to make better decisions in all things home. One key part of this is to provide experiences to give buyers a genuine feel for what a home is like. Photos, they often go through some serious touch-up work, and while more recently videos have started showing up, they are still largely curated. And so we went ahead and built 3D Home to address this objective. So 3D Home is a tool that allows buyers to first experience a first-person walkthrough of a home before visiting it. It allows for quick triage so shoppers can spend time visiting the homes that they care most about. And the final objective is that we want to provide an experience that's easy to capture, quick to process, and fun for users and the captures really to explore. Let's talk about our main goal for the project. For consumers, we want to give them a sense of control. We want to make it so they're able to trust what they're seeing. For the content creators, the photographers, we want to give them something that's low cost or free, and that is easy and an engaging experience. And so to accomplish this, we built a viewer experience to allow shoppers to walk through a home on their own. We included arrows between rooms and menus and thumbnails to quickly jump between rooms and floors. These are the main components of the tour, the 360 image for each room that a content creator captures either on an iPhone or a 360 camera. There's connections that allow you to move from room to room, thumbnails to give you a preview of the room, show your current room, and quickly jump to an unconnected room. So to give you a better idea, here's a short video about the product.
These days, home shoppers have the upper hand with advanced digital technology catering to their needs. Shoppers are increasingly buying sight unseen, so it's more important than ever to provide an immersive inside look at homes. The Zillow 3D Home app is a free tool that makes it easy to add virtual tours to your Zillow and Trulia listings. Just capture panoramas of each room and connecting hallways with your iPhone, and the app stitches them together to automatically build a virtual tour for you. No complicated uploading or photo editing required, allowing you to create an engaging listing and provide the detailed imagery that buyers and renters want. The tours are automatically stored in the 3D Home dashboard and can be uploaded directly to the listing in minutes, or shared with your team to manage the listing. The app can also connect to certain third-party 360-degree cameras to easily create panoramas for a faster capture experience. The 3D Home app lets you create an immersive media experience that helps attract more buyers, sellers, and renters. Then they can arrive at showings more informed. Get started today by downloading the 3D Home app.
And so for our requirements, we need to take a set of 360 panorama images and compute the connections between them, which we'll call PVC for the rest of the talk, to indicate pano visual connections, and thumbnails and other image assets. We bundle these results together to provide a viewer experience that gives a consumer the feeling of walking through a home. There's two options for image capture. One with the iPhone, capture a panorama like you normally would, which captures a video that must be processed into a single 360 image, or you can connect a 360 camera that stitches on the camera itself and provides a 360 image as an output. What are connections? It's fairly straightforward. Imagine you capture one panorama in a kitchen and another panorama in an adjacent living room. The goal of detecting connections is determining if those two panoramas share a bit of visual content, meaning that if you can see one panorama from another. Ultimately, what we want to compute is the relative angle from one image to another so that we can automatically jump from one panorama in the viewer to another and end up where we expect to be in the home. So how do we do this? We use something called feature matching. That's a computer vision technique that involves finding interesting points in each image, such as a unique spot on the wall, corners of cabinets, etc. We mark these points on each image. Once we have these features for each image, we can compare the features across the images and see if features match with one another. The more features that match, the higher confidence that we have that those images are connected to each other. The second part of generation includes generating thumbnails and other assets. Since the image we get from the user is a 360 image, it becomes pretty hard to visualize what a panorama might look like outside the 360 viewer. We want to make it easy to understand what is going to be in a panorama before actually jumping into it. In this way, we're creating a sort of preview image in the viewer. How do we do this? We can imagine a 360 image as being wrapped onto a sphere. What we want to do is then take a section of the spherical image, map it onto a 2D plane that's more easily understood on a flat screen. In other words, we're unwrapping part of the sphere to create a 2D flat image that looks good on a screen. And so what's our end-to-end look like? So starting from a 3D home iPhone app, the user captures the panorama with their iPhone or the connected external 360 camera. If they're using an iPhone, we'll stitch the image together on the phone, whereas on a 360 camera, the image is already stitched together on the camera. These images are uploaded to our S3 bucket. At the same time, the app is communicating with our data service API via a mobile proxy service that provides auth. After all of the images are uploaded, the app will tell our API that the tour is ready for processing and will kick off a processing task, which is indicated by the processing black box on the right. We use DynamoDB to keep track of our rich metadata for the viewing experience, such as floors, connection angles, panoramas, etc. Whereas we use an MS SQL database for our relational models that also allow us to interface easily with other Zillow infrastructure. So what we're going to focus on for the remainder of this talk is the black box processing pipeline. Each tour has a workload that scales quickly by the size of the home and the number of captures taken. It scales linearly for thumbnails since we are generating a constant set of thumbnail assets for each panorama, and it scales quadratically for the connections to cover each pair of panoramas. Each of these are computationally intensive processes. So we started brainstorming solutions to these tasks and came up with a traditional task queue and polling mechanism that's been pretty popular for years. Our data API would push tasks onto a work queue powered by AWS SQS and a cluster of EC2 instances that would pull the queue and pick up tasks to work on. In the diagram on the right, our data API pushes data to SQS, and our processing cluster picks the task up and communicates its progress back to our data API. We can see the communication protocol here. This diagram highlights the status tracking and the task dispatching protocol of our prototype design. Our data API pushes a job to SQS. The processing cluster will grab the task and tell our data API that it did so. The processing cluster then launches its computational subprocess, which will upload the generated image assets to S3 and return the connection as a JSON to the cluster when it's complete. The cluster will then tell our data API that the task was complete and update the status of the tour and tell the end user that it's done. This process is repeated for each computational unit, that is, every thumbnail generation for a single panel or connection detection for a pair of panos. After the subprocesses have complete, our data API does some last-minute processing to prepare the tour for consumption. Given the number of computational units for a single tour, this is a pretty chatty protocol and becomes a little messy and to get a sense of the current state of tour processing. So while this architecture definitely works, it has certain disadvantages. First, it's very costly because these tasks are extremely computationally intensive, requiring beefy hosts to deliver a timely output for the end user. Our workload is very sporadic, and users have an expectation of quick processing and previewing of their tours. Because of this expectation, auto-scaling didn't quite fit our use case perfectly because spinning up and tearing down takes up valuable time that the user spent waiting. As illustrated in the previous slide, it can be hard to maintain because of the chatty protocol, which made it difficult to really understand the execution status of a tour. We had to build different dashboards to monitor the tasks, and we manually had to implement retry logic. And finally, we had to contend with sort of the day-to-day operational burdens of managing our own hosts. And so with these challenges in mind, we went back to the drawing board to see if we could create a more robust and scalable and budget-conscious solution that would meet our needs and the needs of our customers. These are some things that we had in mind. So some of the options we considered were considering reworking our architecture with a new custom orchestration service. It was going to be pretty costly. We didn't really want to maintain our own services. And other solutions we considered seemed like they'd be great for orchestration, but we'd have the same problems of having to take care of our own computational load balancing and figuring out a scheduler and maintaining that scheduler. So ultimately, the winner was AWS Step Functions. And with that, Nikhil is going to talk about the next chapter of our product's architecture.
Hi, my name is Nikhil Gupta, and I'm a software engineer at Zillow on the Rich Media Experiences team. I'm going to walk you guys through the basics of step functions for those less familiar, but then quickly dive deeper to cover how we created our processing pipeline to be robust, scalable, and easy to monitor. So what are step functions? Step functions are a workflow orchestration framework powered by AWS that allows you to easily coordinate multiple AWS services into serverless workflows. So they're instantaneously available when you need them, completely serverless, they integrate well with other AWS services, and they're easy to extend and modify. They also allow for built-in retry logic and give you a very nice dashboard to monitor the status of any given execution. So how are step functions defined? They're defined using basic JSON using the Amazon States language, and they consist of the individual states that you define as well as the transitions between them. You can see an example on the right here that we'll dive into a little bit later. So let's talk about states. So states are the basic building blocks of your step function. So echoing back to your computer science theory classes, a step function is basically a finite state machine that allows for transitions between different states. The states in that state machine are similar to those in step functions. You define the way to enter a state, and you define where to go when a state is complete. Each state can perform some operation to manipulate its input. And so AWS provides many different types of states to allow you to perform various types of work. The current list they provide are listed here. So let's walk through that example definition from earlier. So in this example, you can see the start state that is going to output some data. In this case, it's outputting an array under the key vals. The next state is a filter state, which takes that vals array as its input and filters out the first element of that array. Once that output is complete, it will end the step function, and the final result from the step function would be output. So now that we know how states transition from one another, you may be wondering how actual work is done. That's where task states come in. These can take input from the previous state and dispatch a computational action, which can consist of many different services that AWS provides. For example, you can invoke a Lambda, send SNS messages, etc., that will take in the input to the state, perform whatever operations you desire, and then return the results back to that state. This is important because it allows us to compartmentalize our computational units, giving us more maintainability. It also allows us to be completely serverless during an execution because we only pay for the resources we use. Another key building block in migrating and scaling our workflow are parallel states. This state type allows you to branch and run multiple substate machines in parallel. You define each branch you want to execute as part of your state machine definition, and AWS will take care of executing them at the same time. When all your branches are completed, the results from the branches are aggregated into an array, with each element being the results from a single branch. The order in which you define your branches is the same as the order of the results in the array. The use of parallel blocks is super important in allowing you to create scalable solutions with negligible additional costs. Let's say you had 100 tasks to complete in a single step function execution. You would basically be paying the same amount to run 100 lambdas to process these tasks serially versus running 100 lambdas in parallel. Although it is worth calling out the need to understand and appropriately set your concurrency limits to avoid running out in your account. So how do you loop in your step functions? So sometimes you'll need to loop through multiple tasks and perform the same operation on each. The iterator pattern is a well-known and commonly suggested workflow, and one that we use heavily. The way it works is you have some input that you want to iterate over that gets passed to an iterator state. Usually the state will be a lambda that will perform some work to move yourself forward. Then you'll have another state that checks if you are done with the loop. This state is a choice state, another type of state that AWS allows you to have. The choice state is a simple conditional that allows you to branch based on the value of some variable in its input. In this case, the state will check if you are done or if there is more work to be done. If you are done, it will move to a done state, and if not, it will go to a state to do the actual work. In the example, we have a state called configure count, which will set a target value and the current value as two different keys. Let's say the target value is 5 and the current value is 0. The iterator will increment the current value and pass the result to the isCountReach state. This state will check if current is equal to target, and if so, it will move to done. Otherwise, it will move to example work with the current value of 1. We will then go back to the iterator, which will increment and do the same thing again. So let's go back to the problem that we have and try to use these components to build up to our current solution. Again, we have two key workflows that we need to accomplish. Going more in depth, they are thumbnail generation and PVC generation. For thumbnail generation, we need to create a flat thumbnail image as well as lower resolution images for low bandwidth devices. We also generate tiled images to progressively render higher resolution bits of an image for smoother performance on our front end rather than loading an entire image at once. This workflow requires one execution per panorama. For PVC generation, we need to determine if two panoramas are linked to one another. In this case, we need one execution per pair of images. Both of these tasks can run independently of each other and so work well with the parallel branches we talked about. So here is a visual depiction of our key workflows and how we've implemented them in our step functions. Ignore the branch picker state for now, as we'll go over that in a little bit. What we have here is essentially identical to the iterator pattern we discussed earlier, with the addition of a choice state before iterating. The difference between these two is only on the first execution. In the earlier slide, we would iterate and then process our result, but in this case, we would process and then iterate. This means we must provide the first payload to process as the input to the choice state. Our logic blocks simply take in a payload and do the actual work of generating thumbnails or detecting PVCs. So how do we provide this payload to our workflows? This sounds like a task state that needs to do real computational work, which means it's probably powered by a lambda. In our case, we have two lambdas that do this work, one for each workflow. All each lambda does is download an input manifest that the iOS app uploads, containing information about the capture, including the list of panoramas and their S3 keys. With this information, they generate one payload for each task that needs to be executed and outputs a list of these payloads. These lambdas are part of the same deployment package as two separate handlers within the same CloudFormation stack. The only difference between them is the actual payload they generate. So on this slide, you can see an example of the output of a thumbnail splitter. This is showing two different payloads that need to be processed. Each payload represents a different panorama that needs to have thumbnails generated with it, including the S3 key of the image file and the output prefix where all results for this pano should be stored. This is basically a task queue that can be worked on one at a time or in parallel. Now that we have the pieces together, we can build an end-to-end workflow. So this is what an end-to-end state machine looks like for processing thumbnails alone. We've combined a lot of the components from earlier to create a state machine that includes parallel branches and the iterator pattern to allow multiple workers to process the task queue at the same time. The splitter will output a list of tasks that need to be completed, and each branch will then take tasks off of that queue. The way this works is that the branch picker stage at the beginning of each branch will take that index's payload off of the task queue for the first execution. On subsequent executions, the iterator will pull the current index plus the number of branches in total to make sure that multiple workers don't pick up the same tasks. In this case, the 0th branch would work on index 0, 5, 10, 15, etc., and branch 1 would work on 1, 6, 11, etc. Once there are no more tasks that a branch can pick up, that branch would move to its complete state. Once all branches are complete, we would transition to the end state, which would output an array of all of the results aggregated from the branches. So although this setup worked for us at first, we realized there was one thing we overlooked. The step functions have a max payload size that you can pass between states. This limit is 32 kilobytes, and given the payloads we showed you earlier, we hit that limit at around 80 panoramas. At 80 panoramas, a splitter would output a task queue that was too big to pass to our branches, and our executions would fail. From this, we learned how important load testing was, since most users don't produce 80 panorama tours and we had never tested one ourselves. After that, we added very large pano tours as part of our integration test to make sure we can support any number of panos that a user submits. So how do we solve this? AWS recommends a backing store in S3 or DynamoDB to store data that would be passed between states. For S3, you would pass the S3 key of the data to the next state, and for DynamoDB, you would pass the partition and range keys. For our solution, we decided DynamoDB was a better solution because it gave us the built-in ability for conditional reads and writes, which is valuable for our workflow, as I'll go into soon. So in this case, each splitter will now create an input in Dynamo and populate it with a set of inputs that must be processed. The iterators now pull the item that needs to be processed from this Dynamo item and outputs its result into the same item. So this is what a single item in DynamoDB looks like in our new task queue schema. The input is the list of inputs that are either waiting to be processed or currently being processed. In this case, key 2 is unassigned to any branch, meaning that any branch can pick up this task. Key 3 is assigned to branch 0, meaning that branch 0 is currently working on this task. Setting this value prevents other branches from picking up this task. Similarly, key 4 is assigned to branch 1. Within these top level keys, there is another inner key called input, which is the actual payload for this task. This is what will be passed to the logic block to actually do the work we need to do. We need to be careful here and make sure that our order of any operations with DynamoDB works flawlessly and handles failures at any point in a branch. We also need to make sure that two iterators don't pick up the same task, which I already mentioned our solution to earlier. So how do we build this for resilience? First, let's take a look at all of the steps that need to happen in the iterator, which is the lambda that will be storing the output of our previous logic block's execution and also pulling in a new input to pass to the execution of our logic block. The current state of the DynamoDB item is on the left, and the input to the iterator is on the right. The first thing we need to do is save the output of our previous logic block's execution. This is simply taking the current task key for our iterator and the module output that our logic block spat out and sticking them in the output dictionary within our Dynamo item. The next thing we need to do is delete our input from the list of inputs since we no longer need to process it and don't want other branches to even consider it. Finally, we need to grab another input. The key here is that we need to grab an input that is not being worked on by another branch. We do this by simply grabbing a list of all of the inputs and finding one that is unassigned to a branch. As is, this can lead to an issue if two iterators run at the exact same time and try to grab the same unassigned input. Imagine the scenario where both iterators have both put their previous outputs into the Dynamo item at key 3 and key 4. They then want to pick up another task. If they both read the item as it currently is, they'll both see that the branch name for key 2 is null, meaning it's unassigned. They'll both try to claim that branch and will have some unintended consequences as both try to work on the same task and overwrite each other's results. However, with DynamoDB's conditional expressions, we can easily avoid this. In fact, we can do all of the operations that an iterator needs to do in a single operation. And this was the reason that we chose Dynamo instead of S3. So there's a lot going on here, so let's try to break it down. At the beginning of the iterator's execution, it will read the current state of the DynamoDB table and choose its next input from that by picking a random unclaimed task. For it to successfully claim that task, though, it must not be assigned to another iterator by the time it writes to the table. We do this with a conditional update item. DynamoDB allows you to provide conditional expressions that allow you to define conditions for an operation to be successful. If the server sees that a condition is false, it will not perform the operation and will return an error to you. In our scenario, the condition we need to check for is that the branch name of the new task we wish to claim is null, meaning it's unclaimed. We also need to check that the key exists in the first place. It's possible, though unlikely, that another branch picks up a task, completes it, and writes out the output and deletes that input while in our current iteration and our iterator thinks it's up for grabs. To solve this, we set an attribute exists condition to check that the key still exists, and set an attribute type condition to make sure the branch name is null. If the update fails, we know to read the DynamoDB object again and try again to select another input. If you want more information on what the rest of the hash signs and other parameters here mean, we recommend you check out the DynamoDB docs on the AWS website. So on the last iteration of the iterator, we write out our input and see that there are no more unclaimed inputs for this branch to pick up. In this case, we set isComplete to true to indicate to our choice state that this branch is complete. So going back to our end-to-end workflow for thumbnails, we can now understand what an execution would entail. The output from here would no longer be the actual payloads from the logic blocks, since those are now in Dynamo. Instead, we will output the partition and range key for the Dynamo object so we can go in and process the results later. We can add both of these workflows together so that they all happen in parallel. With this setup, the entire processing of a single 3D home is contained to a single execution that is extremely easy to monitor. Each splitter will output a different item to DynamoDB, and each set of workers will work off of those items. You can see here that we have nested parallel blocks. One parallel block to split into our PVC workload and our thumbnail workload, and another set of parallel blocks within each workload that allows us to scale how many tasks we process at once. In this diagram, we'll be processing 2 PVC tasks and 2 thumbnail tasks at any given moment. Once all of the tasks are complete, we then need to aggregate the results. So after both workflows are complete, we then have a different lambda called the joiner that will aggregate the results. This joiner communicates with our data API to tell it that the task is complete, and it also writes out a S3 object with all of the results aggregated together. The reason we save it in S3 is because we can then use Dynamo as exclusively a processing storage system, and S3 as our longer-lived storage for front-end viewing. We then put a TTL on our Dynamo item so it automatically deletes. So we showed 2 branches in each workflow, but there's no reason we can't scale out as much as we want. In fact, we currently have 20 branches in our PVC workflow and 5 branches on our thumbnail workflow. The reason is because PVC scales quadratically and thumbnail scales linearly, so we have balanced our workers accordingly. This works extremely well for us. The only issue we've seen with this approach is that it becomes increasingly difficult to monitor your tasks from the AWS console when they are so wide, but it's easy enough to zoom in and monitor any individual branch if desired. So let's talk about error handling for a second. So step functions allow you to retry a task on any given error, and you can specify the types of errors that you want to retry on. In the JSON schema for your step function, you can even include things like the backoff, the number of retries, etc. And you can even do catch-alls or catch specific errors. We learned 2 major takeaways from this error handling. The first is that you should always catch AWS service exceptions and retry on them. AWS service exceptions are specific errors that are thrown when things like Lambda is down for some reason or S3 is down for some reason. Things that are out of your control that are probably just transient issues that you should retry on. The second key takeaway is that you should throw custom errors in your code for retryable versus non-retryable errors. If for some reason a network issue occurs in your service, you might want to retry on that in case the network is back up. But if you have an actual error where your data is not where you expect it to be or something like that, you might want to hard fail so that you can investigate further. So error handling is nice, but you need a good way to be notified about them, especially if error rates or resource usage exceed acceptable bounds. Step functions integrate nicely with CloudWatch, as do Lambdas in most other AWS services. We set up various thresholds on Lambda failures, concurrent execution limits, etc. We've also set up alarms on step function failures so we know when a user's Tor has failed to process. Our common way of getting these notifications is by having our CloudWatch alarms publish a message to an SNS topic. We then have our Teams incident management system, which is currently optional, subscribe to these alarms and alert our on-call about any failures that occur. We also have it post in our Slack channel for visibility. Another very important and useful technique we make use of is called Lambda aliasing. All Lambda functions have versions, and every time you deploy your Lambda, a new version will be created. What's important though is you can assign an alias to these versions. In our case, we label them v1, v2, etc. When you define your step function, you can have your task states point to a qualified ARN, which is the ARN for a particular alias for your Lambda function. If you have v1 deployed for your lambdas and you wish to make a breaking change to your data schema, instead of having to deal with backwards compatibility, you can make an atomic switch of your step function. How this works is you ship all of your lambdas with a new alias. In this case, we'll call this alias v2. Your step function will still be executing its current definition, which is pointed to v1 of all of your lambdas. Once all of your v2 versions of your lambdas are shipped, you can then change your step function definition to point to the v2 lambdas all at once, allowing you to create an atomic deploy without any backwards incompatibility issues. So we launched this architecture about a year ago, but we haven't stopped there. We're deep in extending our workflow to take advantage of SageMaker to help us build richer, smarter tours by plugging our step function states directly into a machine learning model. Additionally, we started integrating a new workflow to further use our computer vision technology to generate a corresponding floor map. We can't talk too much more about this yet, but we started piloting it on some home listings in the wild. And finally, with the recent announcement of dynamic parallel workflows, we've gone ahead and reworked our core state machine. We're still currently testing and iterating on this version to make sure we get everything just right. We still have some considerations in state input size that we need to work with, thus requiring some custom iterator work and augmenting our workflow assignments with DynamoDB. Here you can see some of the next steps we're taking. Also, here is a sneak peek of our step function with dynamic parallelism in place. With this setup, it's much easier to diagnose what's going on in any given branch of your step function. Plus, you don't have to worry about the number of workers you want to scale out, as AWS does that for you. Again, there are still some issues we're working through, but we think this is a big step forward for creating a scalable architecture that you don't have to think too much about. Now we'd like to show you a quick walkthrough of how we can use a step function dashboard for easy debugging and monitoring.
So this is the step function dashboard, which is the central monitoring location for your step functions. This is the view for the step function that we just discussed. You can see a list of the executions as well as the definition and the tags for the step functions directly from within here. So as we scroll down, you can see a list of the executions as well as their statuses. You get a quick view of whether they were successful or not. So if you get a notification that one has failed, it's very easy to find the failed execution and debug it. So if we want, we can even filter by a certain execution type to help us find a specific execution even faster. So let's click into one of these successful executions and examine it further. So on this page, you can see information related to this execution, but the most important thing is the visual workflow, which shows the actual execution in a nice diagram. So we can expand it to get a little bigger, which really helps given how wide our step function is. Here green means successful and red means failed, so you can quickly find which state failed in any given execution. So zooming in, we can see the PVC branches we talked about earlier, as well as the thumbnail branches, and that they were all successful. We can even see the joiner being successful, and scrolling over, eventually we can see the error handler and the fail end state. The error handler was not called because there is no error, which is good. So let's go back and take a look at a failed execution this time. So if we zoom into this one and scroll over, we can see that the error handler was actually called this time. And if we open up the input, we can see that we can see the error directly from within here. And in this case, our data API returned a non-200 code, so it's a good thing we errored, so we can go investigate that further. Another useful part is the execution event history. And scrolling down, you can see every single state transition that's happened in the state machine, as well as the inputs and the outputs. This is super helpful when debugging in case one specific transition failed and you want to know which input failed. And finally, let's talk about lambda aliasing again. So on the dashboard itself, we can edit the step function definition. So here you can see the actual JSON definition fully, and you can see all of our states. And so for a particular resource, we can see the lambda version and the lambda ARN that's put in for this lambda. And specifically, you can see the qualified ARN, which includes the version. We can change this to whatever we want and make it be effective all at once. And you got to make sure you do this all for all of your Lambda definitions throughout if you want to make an atomic deploy. So let's go ahead and change this to v2. Let's save. This will give us a warning. And it would just now be immediately effective. But now we'll just put it back to v1 so we don't actually break our step function. And shifting over to the Lambda side of things, we can see at the top for the Lambda on the dashboard the qualifiers, which is the versions and the aliases for this Lambda. So in the versions, you get a new one every time you deploy, and we can see the alias assigned to that version. And if we click on aliases, we can find all of our aliases. And this is what we put after the colon on the step function definition to indicate which version of the Lambda we want to run. So this is super important because it allows us to deploy different versions and not actually break or use the version until all of our dependencies are ready.
So we hope you learned a little bit about AWS serverless and our transition from a more traditional architecture to one powered by step functions. If you have any questions, feel free to contact myself, Nikhil Gupta, or Randy Yao at any of the email addresses listed here. Thanks.